Welcome to Understand the Math. This video is part of a series of videos on linear algebra and its applications and covers section 2.2 part 2 on elementary matrices and the algorithm for finding the inverse of a matrix. I'll walk through example problems so that you can see exactly how to find the inverse of a matrix. Be sure to check out the link below for free guided notes that you can highlight and fill in as you watch this video. Elementary matrices are special matrices that are derived from the identity matrix by performing a single elementary row operation on the identity matrix. In my video on section 1.1, we saw that there are three types of elementary row operations: replacement, interchange, and scaling. We're going to do an example so that we can see how an elementary matrix can be derived from the identity matrix by using each of these three row operations. In the first example, we'll use this row replacement operation to create an elementary matrix. We'll multiply row 1 of the identity matrix by 2 and add it to row 2, and we'll get the elementary matrix 1, 0, 2, 1. In the second example, we'll do a row interchange and swap rows 1 and 2 of the identity matrix. This gives the elementary matrix 0, 1, 1, 0. In our third example, we'll do a row scaling and we'll multiply every entry in row 2 by 3. This gives us the elementary matrix 1, 0, 0, 3. Let's now see how we can use these elementary matrices. Multiplying a matrix A by an elementary matrix is the same as performing a row operation on matrix A. Let's look at an example to see how this works. We're going to use row operations and then multiplication by elementary matrices to reduce matrix A to the identity matrix. To save some time, I've already written down the row operations that we need to do to reduce A to the identity matrix. What we're going to do now is find the elementary matrices that correspond to these row operations. If we look at the first row operation, minus 3R1 plus R2, the elementary matrix that would do the same thing as that row operation is 1, 0, minus 3, 1. And that results from multiplying the first row of the identity matrix by minus 3 and adding it to the second row. Let's now look at the second operation. For this operation, we're going to divide row 2 of the identity matrix by minus 2. So our elementary matrix is 1, 0, 0, minus 1 half. For our third row operation, we'll multiply the second row of the identity matrix by minus 2 and add it to row 1. This gives us 1 minus 2, 0, 1. Let's now see how we can use these elementary matrices to reduce A to I. What we're going to do is multiply E3 times E2 times E1 times A, and when we do that, we'll get the identity matrix. Notice that the order is reversed. We first have to multiply E1 times A, and then E2 times what we get, and then lastly E3 times what we get. And that gives us the identity matrix. We're now going to use the elementary matrices that we just learned about to develop an algorithm for finding A inverse. The idea behind this algorithm is that, just like we saw in the last example, multiplying a matrix A by elementary matrices can reduce it to the identity matrix. If we need k row operations to reduce a matrix A to the identity matrix, we need to multiply that matrix by these elementary matrices. If we multiply both sides of this equation on the right by A inverse, we get the same elementary matrices on the left, multiplying the identity matrix because A times A inverse is the identity, and then on the right, we just get A inverse. This tells us that we can use the same row operations on I that are used on A to get A inverse. This leads us to our algorithm for finding A inverse. To find A inverse, all we're going to do is augment A with the identity matrix, then use Gauss-Jordan elimination to reduce A to I, and then I to A inverse. The diagram that I've listed here is going to make this algorithm easy to remember. You start by augmenting matrix A with the identity matrix, perform Gauss-Jordan elimination, and use the same row operations on A and on I, and then you end up with I on the left and A inverse on the right. Let's make a note that if A cannot be reduced to the identity matrix due to obtaining a row of zeros, then we'll know that A is not invertible. Let's now walk through two example problems so that we can see how this algorithm works. We'll use Gauss-Jordan elimination to find the inverse of these two following matrices. Let's look at our first example. We'll begin by putting A and the identity matrix into an augmented matrix. This gives us the matrix 1, 1, 2, 1, 2, 1, 2, 1, 2 on the left, and then we're going to augment it with our 3 by 3 identity matrix 1, 0, 0, 0, 1, 0, 0, 0, 1. We'll start with the forward phase of the algorithm. This is our first pivot, and we need to get zeros below that pivot. We'll take row 2 and replace it with row 2 minus row 1, and then we'll take row 3 and we'll replace it with row 3 minus 2 row 1. We'll perform both of those operations on both sides of the matrix. This gives us 0, 1, minus 1, minus 1, 1, 0, and then 0, minus 1, minus 2, minus 2, 0, 1. We'll circle our next pivot, and then we'll go and we'll get a 0 below that pivot. For this one, we only need one row operation, and for that row operation, we'll take row 3 and we'll replace it with row 3 plus row 2. This gives us the matrix 1, 1, 2, 1, 0, 0. The first two lines are the same. And then the third one changes. We'll get a 0, 0, minus 3, minus 3, 1, 1. Let's now circle our pivot. Before we begin the backward phase, we need to make that pivot a 1, so we'll take row 3 and replace it with row 3 divided by minus 3. This gives us the matrix. Again, the first two rows are going to stay the same. And then the third row gets divided by minus 3. It's pretty common when you're finding A inverse that you're going to end up with fractions. Let's again circle that pivot, and now we can go about getting zeros above that pivot. This is going to take two row operations. We're going to take row 2 and replace it with row 2 plus row 3. And then we're going to take row 1 and replace it with row 1 minus 2 row 3. Let's see what we get. Because we're starting the backward phase of the algorithm, we're going to write the bottom row first. 0, 0, 1. 1 minus a third and minus a third. And then we'll write our second row. That becomes 0, 1, 0. 0, we get a 2/3 and then a minus 1/3. Our top row is then 1, 1, 0. And on the right, we have minus 1, a 2/3, and another 2/3. Hang with me, we're almost done. Let's circle our pivot. And now the only thing we have left to do is to make that 1 a 0. To do that, we're going to take row 1 and replace it with row 1 minus row 2. This is going to give us the identity matrix on the left. Our second row looks like 0, 1, 0. 0, 2/3 minus 1/3. That doesn't change. And now it's just our top row that changes. we get a 1, 0, 0 on the left, and on the right, we end up with a lot of cancellation, and we get a -1, 0, 1. Our left-hand side is the identity matrix, and our right-hand side is A inverse. Usually when you're working problems like this, it's best to write down your answer all by itself. So we can say that our A inverse is -1, 0, 1, 0, 2/3, -1/3, and then 1, -1/3, and -1/3. These calculations are really long, but it's really worthwhile to practice these so you'll know exactly what to do. We're going to do a little bit more practice and look at a second example. In this example, we're going to end up with A inverse being undefined. And I want to go through this so you can see exactly how that happens. Just like in number 1, we're going to take A, we're going to augment it with I, and that's always our starting point. We have 1, 6, 4, 2, 4, -1, and then -1, 2, 5. And on the right-hand side, we have our 3 by 3 identity matrix. Just like we did in the first example, we're going to circle our pivot, and then we're going to go about getting zeros below that pivot. Our row operations are going to be row 2 goes to row 2 minus 2 row 1, and then our row 3 is going to become row 3 plus row 1. When we do both of these operations, here's what we end up with. Our top row stays the same. And then our second row is going to change, and it becomes 0, -8, -9, -2, 1, 0. And then our bottom row becomes 0, 8, 9, 1, 0, 1. Let's circle our pivot, and then we're going to get a 0 below this pivot. We're only going to have to use one row operation to do that. We're going to take row 3, and it's going to become row 3 plus row 2. This gives us the matrix. Top row stays the same. Our second row stays the same. And then our last row changes. It becomes 0, 0, 0. And then on the right-hand side, we get -1, 1, 1. You can see on the left that we have a row of zeros. Because of this, this row of zeros is never going to become a row with 0, 0, 1. Our matrix A cannot be reduced to the identity matrix. And we say that A is not invertible. I want to call one more thing to your attention. Notice up in our second matrix that these two rows are multiples of each other. Whenever this happens, you can know that one of those rows is going to go to 0. And if you notice that ahead of time, you can just go ahead and stop there and know that A is not invertible. Be sure to check out the next video in this series where you'll learn all about the properties of inverses and how to solve matrix equations.
If this video has been helpful to you, please consider subscribing to my channel. Keep believing in yourself and have a great rest of your day.